All right. Hello and welcome. For those who have joined us before, welcome back. And to any newcomers, we're excited to have you join us today. My name is Abby Harrison, and I'm the Starlab research lead at OSU. And today I'll also be your host and moderator for this workshop. Today's workshop is a part of our ongoing Bioastronautics Research series hosted by Starlab Space and the Human Performance Collaborative. Every month, we meet up to explore a different topic in bioastronautics research and learn from both industry and academic leaders in that subfield. So today we're going to be discussing design and development of space habitats, and then next month we will have a session focused on space medicine. I'd like to start out with a quick run of show for today's event. The event will be 2 hours long. I'll start by sharing a quick introduction to Starlab. I'll then hand the microphone over to Josh Hagen from the Human Performance Collaborative to tell us all about HPC and the work they do there. We'll then have 4 presentations from some really incredible speakers across both academia and industry. And then following that, we'll have a panel discussion and audience Q&A. So throughout the session and throughout all of the presentations, feel free to share questions in the chat or to hold on to them to ask independently at the end. We will be addressing all questions during that Q&A period at the end, so not following each individual speaker's presentation. During that Q&A period, you can either drop your question in the chat or you can raise your Zoom hand, and we will unmute you to directly ask that question. All right, so I will jump in and just share a little bit more for those who are new to our community about Starlab. Starlab Space is a joint venture formed of companies from all around the world that are working together to build the Starlab commercial space station. Starlab was selected by NASA as a Phase 1 recipient of the Commercial Low Earth Orbit Destinations Program to provide ongoing research and human habitation capabilities following the retirement of the International Space Station at the end of this decade. The teams at Starlab and all of our partner companies, which include Voyager, Airbus, Mitsubishi, Palantir Space Application Services, Journey, Hilton, MDA, and of course, The Ohio State University, have been really hard at work building a next generation space station for the benefit of all on Earth, and we plan to launch in 2029 on a SpaceX Starship. We're all very passionate about continuing and improving research in low Earth orbit and are excited to be connecting today with all of you to talk about the future of human habitation and design of space habitats. So if you have any more questions about Starlab or want to discuss further, feel free to reach out to me. My information is on the registration website that you all have access to, and I would love to discuss more about Starlab. But that's not the point of today. So instead, I will go ahead and pass things along to Josh Hagen, who's going to be sharing a little bit more about HPC with us before we jump into our speakers. Josh, take it away.
All right, great. Really appreciate everybody for joining today. This is, I think, our fourth edition of this. Yeah, four. All right, thanks, Jack. So I'm the faculty director of the Human Performance Collaborative at Ohio State, and our mission, much like Starlab, is to try to facilitate and execute really, really awesome multidisciplinary research to, in our case, advance human performance for all humans on Earth and off of Earth now with Starlab. So it's really, really fun. Like there's so many amazing brains and so many amazing ideas across our university and all of your universities, your organizations. And really we want to facilitate that collaboration and the opportunities with Starlab and space research is absolutely amazing. Awesome stuff going on in Columbus, but awesome stuff going on all around the world that we're really trying to connect to. So anything that we can do to advance human performance, human in the loop, habitats, environments for humans to interact with. That's really what we're all about. So excited that you're all here. Hope you enjoy it. Please participate, ask questions, talk to the speakers. They are awesome and they will do a good job of taking care of you. Thanks. Back over to you.
All right. Thanks so much, Josh. Really appreciate that. Yeah, the collaboration between Starlab and the Human Performance Collaboration has just been incredible. And a little sneak peek before I hand it off to Michelle for our first presentation is that next month at our space medicine workshop, it will actually be a hybrid workshop. So we'll have in-person meeting as well as virtual. And for in-person attendees, we will also be doing an afternoon of tours of the Starlab and HPC facilities for any interested parties as as well. So feel free to reach out to our organizing team, and we can work with anyone who's interested in having ongoing conversations and visits with both HPC and the OSU Starlab team. Okay, Michelle, would you like to go ahead and share your screen?
Yes, let's see if I can do it quicker this time than last time.
Beautiful. Thank
Uh,
you for
you,
joining us today.
you can hear my voice and see my screen.
Yep, looks good, sounds good.
Okay, I will apologize. I'm working through a cold at the moment, so my voice is a little haggard. But I am Michelle Schrenk. I work out of New York City, and I work for a company called Journey. So we started working with the Starlab team about a year ago. Our history is in experience design, strategy, and also design across the physical world all the way through the digital. So as Journey, we're here to help create the spaces and places of tomorrow. What's on the screen, we partnered with other groups, including Madison Square Garden and Populous, to deliver the Sphere in Las Vegas. And this is just one of several, kind of key projects for us. We also worked on the Apollo 50th anniversary, the live show and production that was done in DC and projection mapped onto the Washington Monument. So there's really a really big breadth. We're about 400 people between North America, Europe, and the Middle East. And we bring to the table just a wide variety of capabilities. Our studio, specifically in New York, works through a lot of physical design. So our earthly projects here, you can see we work through hospitality, entertainment, food and beverage with real estate developers, healthcare, residential. So we're designing really imaginative spaces, but also really importantly, we're thinking through the human experience and the touch points and the services and the memories that people are making throughout their time in these spaces. We also have a digital studio that works through digital twins. So obviously on a complex space station like Starlab, there's very intricate 3D models. We're also working with the Airbus team to move that into Unreal, which is a gaming engine, so that users, whether it's Starlab or different commercial tenants, essentially, they're able to preview and train and use a digital environment in addition to the physical mockups that Starlab is building as well. So before the station launches in 2029, you're spending the next 3 to 4 years having an understanding of how the system will actually work. Because once you're up there, as everyone on the phone knows, just every second counts, every minute counts. Your time is highly choreographed between the team in the station and the team on the ground. There's really important communication channels that need to be maintained. So having people feel comfortable before they're actually in orbit is actually a huge part of this design challenge as well. So as mentioned, we're working with all the partners that Abby mentioned, but especially working closely with Hilton. While Starlab is not a hotel in space, people are not going up there for leisure, at this time. Hilton is known for delivering, great stays and great experiences. So it's important for us to work with all the partners to deliver not only really intuitive design, but also something that helps take care of the humans that are there. So that brings to mind just a really important conversation of where we are in the age of space exploration. So again, as the people on the phone know, the ISS is a heroic effort in the way that it was built and the amount of time that it has been in orbit. It is a time of frontier and exploration. Many of the people that traveled there, it was the first of its kind, but we're now in a new time and age of commercial space travel. So Starlab is one of several competitors that are being developed and replacing the ISS. And that just changes the lens a little bit. There's not just one or two options. There will, in the next 5 to 10 years, be many options. So because Starlab is a habitat and a residency and a workplace to continue the research that's currently been taking place on the ISS, biotech firms, space agencies, civilians, all of these groups will all of a sudden have more choices in who they partner with to go into low Earth orbit. And so that's also our, I would say, filter on this as well, is not just designing a space station that's functional and helps the people within its walls survive. We want to make sure that we're offering a brand forward, very distinct Starlab experience, because people will be wanting to choose the way that they'll choose a Hilton over a Marriott versus any of the other flagship brands. And we also need to be inventing. We know that there were hundreds of things that were invented for the initial decades of space travel. We also need to make sure that we're not just replacing the ISS with a new ISS. We need to be pushing ourselves to develop new products, new environments, new lighting systems, integrating emerging technologies, because the future of space travel is deep space, either to Mars or it's longer stays where you may have civilians and other people going up for more leisure. It's a more accessible space in the future. So we fully recognize that it is, for the designers on the phone today and working with Starlab, we also need to continue pushing the bar. And just to talk about the role of humans in space, in the initial times, astronauts were basically test subjects. They were launched for different durations to test the effects of zero gravity or low gravity on the human body, on how the digestive tract works. And now we're in a phase where astronauts are elite athletes. They're top of their field scientists. They're fighter pilots. There's actually a very low number of people that have been to space. And so it was the age of celebrating the human as the astronaut. And then we're also moving into a future where the human is a customer and eventually a guest. So to just keep drawing the lines between it's a habitat, but it's also a residency, but it's also hospitality. We want to make sure that we're not just keeping people alive, but we're keeping them well along the way, especially as they'll be spending, 6 months at a time there, if not longer. And we also recognize it's important in the whole experience arc of someone going to Starlab. It's not only the time in orbit, which is the current focus, is how are we designing that habitat to do all of the things here, deliver nutrition and exercise and sleep and rest, but there will also be the time that they spend on Earth beforehand and the time after. And this is also what, emphasizes the fact that it's also a commercial endeavor. This is how brands think. This is how experience, designers think as well. Some of these touch points are digital. Some of them are more ephemeral or spiritual. There's these ways to create a more connected journey, where a significant part of it is spent in the station itself, but we have to consider the shoulder times as well. And I'll move through these pretty quick, but this is some of our work with Starlab specifically. In the past year, we've spent time with the astronauts and the ground control, people that have worked at ESA and NASA. There have been so many experts that we've been able to speak with. Because again, before we get right into the design, we want to talk about the experience. So I won't read through all of these right here, but you can see some of these large categories that start to emerge. There's a lot of conversations about productivity and how there's the red line that goes across the screen and it's keeping track of their day kind of in minute by minute intervals. We want to make sure that people are productive, but they also have autonomy. It's also the fact that you can't step outside of the ship at all. You're there with 4 to 8 roommates, and there's really kind of no escaping it. So how do we give people their moments of privacy and wellness and also break up their day? There's a lot of, one of the astronauts said it's not boredom, but it is tedium to some degree. I think there's a lot of celebrating space exploration, through TVs and movies, and people are brave and bold to be out there. But at some point, it does become like living in a 3-story apartment. And so we need to make sure that we're keeping that in mind for how we approach technology finishes and the amount of communal versus private spaces. And I'll just run through these pretty quick. But again, the people on the phone know this really well. The ISS is a miracle, but it's also very cluttered. Any new space station that goes up now will be new. It'll be fresh and clean, but we're also just trying to make sure that we are thoughtful in how we approach storage. Again, technology, how are things replaceable over time? How can we hide the clutter? How can we be smart about cabling and all of the mechanical systems so that it has a life that doesn't burden the occupants just through the clutter and the aggregation, which is going to happen over time. And then we also know that when astronauts thrive, habitat, your environment, makes a huge difference in how you go through your days and your weeks and your months. So there are great innovations happening, in space. And we just want to make sure that the environments that we're delivering play a big part in that. So the act of sending human beings to space is extraordinary in itself, but we want to make sure that we're keeping people well along the way, not just keeping them alive. And just for how we work, again, without jumping straight into the physical design, we want to make sure that we work through mission statements. We want to define our experience pillars. And then we want to make sure that those big ideas reach all of our touch points. So again, Starlab is one example, but there's also VAST and Axiom and Blue Origin. There's a lot of competitors, kind of vying for the funding and for these spots in low Earth orbit. So we're trying to define something that is also uniquely Starlab. Their vision is to transform humanity. So as we think through the experience, to transform humanity, we need to start with the human. Starlab is a next-gen space station designed to elevate that human potential. And then what we've established as our experience pillars, these are essentially like the table legs that hold up the table. Performance grade quality. These are very ambitious people that are going up to space. So we want to make sure that the environment, the products, the technology are as robust and multifunctional as the people are. And we also want to make sure that we're optimizing the whole human. It's not just about making sure, again, that all of the base needs are fulfilled. Creativity, imagination, mental health, spirituality. There's a lot of other aspects that we want to make sure are on the forefront as much as the physical. And then also just the fact that it's mission driven. We want to make sure that every moment up there feels like it's part of a bigger vision. And just some of the categories that we're working through. So again, a habitat is not only, the surfaces and the elements that are permanent and built, it's all of the other systems and elements that get layered on top of that. So we're first focused on the environmental. We're working closely with Airbus on layout, on materiality, on lighting, on mechanical, electrical plumbing. We want to make sure that the things that are priority are what needs to get launched in 2029. We have a couple more years to start developing. There's soft goods, there's case goods. In a hotel analogy, it's the bedding, it's the, operating supplies and equipment, it's the scent. There's a lot of other things that we can layer in, and we have a little bit more runway of time because those can get launched, in future vehicles. But these are just as important. It's what the crew's touching, it's what they're using every day. So there's a lot of opportunity here to think the food packaging or again the sleepwear or the bedding in the crew quarters. And that will help define, again, a much more kind of wellness-oriented and future-thinking brand for Starlab. And then just as our final slide, again, we're working through a lot of the design elements right now. Starlab just had HITL testing in Houston on their high-fidelity mockup. And this is a mix of mood board images and illustrations. We don't have any like renderings to share at the moment, but this just starts to show you kind of the bounds of how we're thinking about the human experience here at Starlab. And I will cede my time.
All right, amazing. Thank you so much, Michelle. That was really incredible. And I loved hearing about the forward-thinking work that Journey is doing to ensure that Starlab is truly a optimized next generation LEO habitation station and ensuring that it's healthy and happy for our astronauts. And speaking of healthy, our next presenter is going to be Dr. Karen Dannemiller, who's going to be sharing some research and work into microbial contamination in space and looking a bit into how we can do better in the future on habitats like Starlab. All right, Karen, it's all you.
Great. Thank you so much for having me. It's really a pleasure to be here, and this is such a great series to bring everybody together to talk about all of this. So my name is Karen Dannemiller. I'm an associate professor here at Ohio State. I'm in engineering and public health, and I study the indoor microbiome. So that's all the fungi and bacteria that are in our environments and cohabitate with us. On Earth, we look at things like childhood asthma, and then we've also been able to work on some projects using dust from the International Space Station. So I'm going to share some of our work related to keeping those environments healthy today. I'm going to start with Earth, and then we'll move towards the implications for spacecraft. So as we all know, we are soon going to have many, many more people living and working in space. And one of the big things that we need to keep in mind is keeping that environment healthy, as you just mentioned, Abigail, because we really need to make sure as we're sending more and more people up, they may have different health status. We really need to make sure that environment is going to support that health, especially in a place where you might have changes to immune system function or other changes where you really need to make sure that you're not going to have extra infections and things like that. So historically, spacecraft have been especially prone to microbial problems. And that's because if you think about it, we exhale moisture, we sweat. Humans are going to inherently be bringing moisture into an environment that can support microbial growth. So the spacecraft Mir, at the time of its decommissioning, actually had fairly extensive fungal growth on things like wiring and window seals, which of course you want those when you're in space. And we learned a lot of lessons when we built the International Space Station, but you can still have unexpected events. So, for instance, this is a panel that was in the hygiene unit where astronauts were hanging their damp towels, and you can see what is potentially fungal growth on there. Unfortunately, this panel was discarded. I'm so sad. I would have loved to have that panel to figure out what was going on. You know, I live in a world where one person's trash is another person's treasure. I'm completely on the treasure side of that equation. But you know, would have loved to look into this more. And so we do need to be careful in these environments where we have absolutely no ventilation and think about having healthy indoor spaces and especially controlling moisture because if we don't, we can have mold problems. So I don't know if anyone here has ever had a mold problem in their house or knew somebody had a mold problem in their house, but it can definitely be a challenging situation with potential health effects. It can be expensive and time consuming. And one of the biggest challenges in this area is actually identifying in some cases if you actually do have a mold problem or not. Sometimes it's obvious and you just need to clean it up, but sometimes you're not sure. And the reason that we have such a challenge is we actually don't have a great quantitative way to detect that. So if you look at this graph, on the y-axis is association with health outcomes, like so how strongly this way to measure mold associates with health outcomes. And on the x-axis is different ways you can measure mold. And all of our quantitative measures here in white don't associate very well with health outcomes. Those are pretty low associations. However, there's a lot of other measurements that associate very well, like do you have moisture in the environment? Do you smell mold? Do you see mold? And so we said we need to be able to do better. We need to come up with a better way that we can identify mold in these environments, which is going to help us here on Earth, as well as in space, avoid those types of health outcomes. So I'm going to fast forward through about 10 years of research. But one thing we realized is that all of these measures down here with the poor health outcomes actually are based on the same fundamental assumption about measuring mold in the indoor environment, that it's some species, it's some bad species, that if that's there, you have a problem. And we said that's actually not the case. So we took actually a completely new approach to measuring mold in the indoor environment by looking instead at function of the microbes, like what are they doing? We're looking at RNA. We're like, what are these things actually doing in these environments? It's kind of like we don't care who's there, but if they're doing bad stuff, we want to know about it. So we used a lot of new techniques to really measure function in these indoor spaces from microbes, which has many applications in mold detection, like I've talked about, but potentially things like asthma prevention, odor prevention, biosecurity, and other things like that. So we did this both on Earth and with some samples from space. So I'll talk about our Earth samples first. So we collected samples from around the country and brought them back to our lab and mimicked different conditions that you might experience in an indoor environment. Some had high dampness, medium dampness, or low dampness. And then we looked at the fungal function in these different samples, the RNA that was expressed. And what we found is that function was actually a really great indicator of if you had a mold problem. So this is a principal coordinate plot where similar things cluster together. So the closer two dots are to each other, the similar those samples were, and the further apart, the more different they are. And what we see is when we look at function, we get really great separation of these circles of the different dampness types if they're low, medium, or high dampness. But when we look at species, like all these traditional measurements do, you don't get that separation. We see a lot of overlap in these circles. What that translates to is that actually this is a really great way that we can understand what the microbes are doing in our spaces and actually use that information to translate it to detecting when we have problems and you might potentially have health outcomes or harmful mold growth in these spaces. You can actually see this too. So these are images taken by Dr. Nick Nastasi. He's a postdoc in my group who will actually also be on the panel today. And you can see at low relative humidity, this is dust on carpet fibers. You don't see a lot of fungal growth here. It's just pretty much dust on there. But as you get to 85 and 95% relative humidity, you start to see things like hyphal extension. And then at 95 and 100%, you actually see fungal fruiting bodies. And this correlates to that functional difference that we see that's actually fairly consistent across the entire fungal kingdom. So we basically don't care what microbes are there, but we care what they're doing and if they're releasing things that are going to be potentially associated with health impacts. This is my favorite GIF. I'm still waiting for it to go viral on social media, so look for it on your Facebook page soon. But basically, we can also look very specifically at the genes that are expressed. This is a KEGG ontology plot where basically we're looking at the different genes that are expressed in these conditions. And you'll notice at 50% relative humidity, we just have a small cluster of genes. These are sort of like core metabolic pathways that these fungi are doing. But as we get to 85%, we have more. And as we get to 100% relative humidity, we have even more. And so as the moisture goes up, we get more gene pathways activated, more of these secondary metabolic pathways. And that's important for two reasons. The first is that these secondary metabolic pathways tend to be where the allergens are produced and the mycotoxins and the virulence factors and all those health outcomes that you care about. And the second is that this provides a lot of targets that we can use to design an assay that's better at detecting mold, both on Earth and potentially in space. So this work is still ongoing. We've identified a list of targets that we're working on that are associated with mold growth in homes, and we're currently validating them. And it looks like we're going to be able to develop a much better mold detection strategy for early indication of when you have a problem in an environment. So that brings me to space. So in space, they have Saturday morning chores just like we do here on Earth. So you can actually see, videos of astronauts vacuuming, in Saturday morning and see all the different nooks and crannies. So I really appreciate what Michelle was just talking about, the visual nature of the International Space Station, that it's all cluttered. And that also provides a lot of nooks and crannies, unfortunately, for dust to settle. And then that's a ripe environment. If you do have too much moisture that becomes present for some unintended situation, that you can start to grow mold. So we have to be really careful about that. But we wanted to do some experiments to see what happens in this dust. So we were able to get some of this dust from these vacuum bags from the International Space Station. Again, I live completely in the treasure side of that. One person's trash is another person's treasure equation. And bring that back to Earth and incubate them under different moisture conditions. And so again, this is a lot of the work of Dr. Nick Nastasi, who's also here, but you can actually visually even see the difference in dust as we incubated it under different conditions as well. So this is at 50% relative humidity, like a typical relative humidity level, and versus 100%, you can actually see even visually just some of that fungal growth that occurs. From this, we were able to do some really great comparisons. We can actually get information on how the fungal communities on the International Space Station are different than those on Earth. So overall, again, these are principal coordinate plots where similar communities cluster together. So you can see the communities on the space station are very different than those on Earth. And we can look at things like diversity, where the International Space Station, this is diversity on the y-axis, and other measures on the x-axis. I won't go into that today, but you can see that there's just a less diverse fungal community on the International Space Station. There's less different microbes that are present. And so even though we have this different community, we wanted to ask, could we still use function in the same way to indicate when you have a microbial problem? And fortunately, the answer is yes. We can still complete these same graphs, and you still get pretty good separation on the function that's occurring at high, medium, and low dampness levels, and you don't really get separation out. We got 4 different bags down. You don't really get good separation by different bags coming down. It's really all about the function. Again, we wanted to take some nice pictures so you can see some of these pictures as well. So the dust is actually pretty difficult to image under the microscope. So we had been imaging carpet for years, and little did we know we were just practicing to take pictures of ISS dust. But you can see this dust. The original dust actually looks pretty clean. I think we're doing a good job up there. We don't see a lot of indication of microbial growth. It looks pretty similar to this carpet from Earth on the right. But when you incubate it to mimic something like a ventilation system failure or a high moisture event, again, we get these fungal fruiting bodies and these same things happening in the dust as happens on Earth, where you're going to start to have these problems. So we were able to analyze this dust as well under different moisture conditions that we mimicked on Earth, and we saw a similar trend in terms of the gene expression that happened, that you get a lot more genes upregulated at high moisture conditions, and we can use that to identify targets that we can use to have an early indication of a problem. So really, we saw that actually the dust from the International Space Station was relatively similar to the dust we saw on Earth. It behaved similarly in terms of function and actually even looks pretty similar to the images we were able to collect from Earth-based samples. So the nice thing is we can use this indicator as a way to develop better systems to monitor microbial communities in spacecraft and make sure we keep it healthy up there. So there's a couple different future directions for this. One is potentially developing the mold sensor that I discussed. This is actually an in-house lateral flow assay that Dr. Nick Nastasi has been working on developing for a dust mite allergen, but you can envision a similar assay that we could develop for mold samples to give you rapid and immediate indication of if you have a problem. So this works kind of like a COVID test, where you put a sample on it and it wicks up the assay and you can tell this, this is different concentrations, but it would look something like this to indicate if you have a mold issue. Other things we can do is think about better ways we can design the spacecraft to make sure we're monitoring for places that dust can be. So right now it's cluttered, as we were discussing, and so we can do things like think about having smooth edges and other things that, while they're also probably going to be more visually appealing, will also have the added benefit of likely making a healthier indoor environment and have less places for dust to collect, and also less time for the astronauts to spend cleaning all of those different nooks and crannies, and just have less risk in terms of if you did have a moisture problem. And then other work we'd like to do is thinking about studying different moisture availability in spacecraft. So obviously moisture doesn't water doesn't behave the same way in space as it does on Earth. So thinking about how these different factors might vary, in addition to not only the water availability, but things like elevated CO2 concentrations, and other things that you might experience on spacecraft and how that would impact microbial growth, to make sure we understand that to keep spacecraft healthy. So overall, we want to move towards using this information on fungal function to support a healthy indoor microbiome, and that's for both use on Earth as well as in space. So we do a lot of studies looking at this to make sure we can keep environments healthy for like kids with asthma, and I think it's going to be similar for spacecraft, that we want to think about what the microbes are actually doing in these environments, and that can help give us an indication of how we can keep them as healthy as possible to support the many, many people who are soon going to be living and working in space. So I have a lot of acknowledgments for this work, of course, the funding agencies, as well as the students and postdocs in my group who work hard every day and are the ones who are working on this specifically. And I look forward to questions and the panel discussion. Again, Dr. Nick Nastasi will be there with us also at the end of this. Thank you.
Dr. Dana Miller, thank you so much. That was absolutely fascinating. And I do agree with you that your metabolic gene expression GIF should go viral. So we'll see what we can do about that. For any participants who were really interested and intrigued by what Dr. Dana Miller shared with us in terms of microbiology and the impacts of microbes in space on human health, we did host a previous workshop series that was all focused on human immunology and microbiome in space, and can make that available, the recording of that available to anyone who wasn't able to join us for that by request. So if you want to learn more about why these types of things matter so much and why human health is different in space than it is here on Earth, reach out to one of our organizing team members and we'd be happy to share that with you. Now we're going to go ahead and jump over and hear from Marta Novak about the architectural challenges and opportunities of designing for space.
Great. Thank you so much for having me. Let me see if I can, oops, share this full screen. Hopefully it works.
Looks good. All
All
right.
right,
Thanks,
very
Marta.
good. Hi, everyone. My name is Marta Novak. I'm a practicing architect and also an assistant professor at Ohio State University. And today I would like to show you some of the design research work that we're doing here with the students of architecture at Knowlton School. And my goal is really to bombard you with ideas and visuals and so on, rather than just looking maybe specifically more in depth at specific case studies, but more broadly looking at different type of approaches and ideas toward design for space station. So with that in mind, before I show some of the examples of the work we're doing, I just want to think a little bit, put everything more in context and zoom out for a second. So if we think about the Starlab, we're thinking about a cylinder that is roughly around 24 feet by 24 feet. And in terms of understanding what that means spatially, maybe another way to think about it would be to think about the volume of 4 American school buses combined together, or 8 shipping containers. So this is the volume that we're working with. But in terms of imagining what kind of human activities have to take place, there is quite a lot. We have to think about work and sleeping and eating and cooking and using toilet and bathroom and communication with family, with NASA and so on, with anyone from outside. So there is just a lot to consider in a very small volume. So how do we think about that? Oof. We understand that ISS have been out in space for quite some time, and we looked at all the images, seeing mostly a lot of clutter. So we want to learn from this and challenge this approach. We already know that engineering allowed us to support humans in space, but maybe thriving is still more of a question. And how do we design around really with humans in center? And this is not anything new. This is not a new idea. We know that from the research done by Valery Polaikov, who was at Mir as a both doctor and astronaut, who was able to conduct research on himself and his fellow crew members. We learn about all the sort of different type of discomforts in space. And NASA, of course, tried to approach this through different interventions, including the Skylab, that included a new type of entertainment stations, dining services, and places for relaxation. Today, when we think about what we understand in terms of the performance, technical performance and design criteria, this could be found in this NASA technical standards, that while it is a document of 400 pages, includes the word design 200 times, I think in my view, still lacks a lot in terms of setting up proper goals and guidelines of what design really means in space. And we also know that despite many, many different studies, both on physical design of humans, psychological understanding of humans and their physiology, I think one big conclusion is that we're very diverse in all these three different matters. So how do we think about space that would accommodate human needs that are so different one to another? And with that in mind, we really focus on these three kind of ideas and explorations, one on the human body, physical human body and ergonomics, one about customization and thinking about personalization, and the last one on the imbalance provisions for collective versus personal space when we design. And I will try to focus on the first two today and showcase some of the work. So we put together this book. This is a 400 pages of research and design research. So if anyone is interested, feel free to email me. I have a PDF of that. That includes a lot of ways of looking at precedents, but also understanding current systems of infrastructure storage, but also understanding human needs and how we view or perceive environment. So you will find a lot of that in it. So the first one, the first category is to look at the human body and ergonomics, so more from like a physical perspective. This is a project by a student, Sophia, who was really challenging the idea of 5th percentile woman and 95th percentile male, and how they would sleep, allowing with the design, allowing all these different type of bodies, both being able to move around during sleep, changing positions, but also allowing all of the bodies to feel equally comfortable. And here a few zoomed in examples, as well as looking at maybe a table design that in space, unlike on Earth, the design is very directional, and in space we can use all sort of surfaces. So for example, here we can look at the table from both perspective, the top and the bottom, that also could be occupiable, but maybe playing different functions. Here you can see the top and the bottom of the table and different uses that could be used, but also thinking about different type of grips that could be supporting movement throughout the station, as well as creating more kind of ergonomic seating that would be adjusting to the human body. We had another student, Devanshi, who was looking at multi-directionality of human objects or furniture, including places for work, or you can just work with your laptop, but also using the other spaces, sides on upside down elements of this as a workspace or as a sleeping pod. In the same way, thinking about this item that could be both used as the chair sitting position, somewhere where you can just hack things with your legs or arms, but also occupy spaces on the inside. But really thinking about this through organic form, but also incorporating softness for comfort. And here, example, a few different objects that you could occupy from all these different directions in many different ways. We had students who were very interested in movement and muscle health, and the idea of like this really big impacts on the muscle mass and the bone density, and basically every single aspect of human body that is affected in space. And his interest really focused on exercise. Right now, we know that astronauts spend about 2 hours per day designated to do exercise within a specific time frame. But his proposal was actually to distribute this exercise throughout the day and incorporate it in a daily into the furniture of a daily basis. So, for example, if we were to use the kitchen, maybe we have the bicycles attached to the chairs. Maybe the chairs are sliding. You have to make an extra effort to use it, but also using this idea of a resistance band and reconfiguring the space for its needs. Some of those also included different handles and grips that would support different use of different muscle groups. And again, thinking through this multidirectionality of different spaces and reconfiguration of it, as well as sometimes, in building in resistance through adding resistance bands for certain activities to again incorporate this idea of exercise throughout the day rather than during designated time. So here you can see the different intervention throughout the specific station. We had students also very interested in medical research and how a surgery will take place in space. And while we're thinking about it right now, it's quite limited, but the idea that in the future, when the missions expand and take longer, performing surgeries and medical procedures would be more needed. So when we think about that research, the students really started thinking about the idea, starting with the idea of the body and how it actually works through different positions and being both sometimes in compression, sometimes in tension, and sometimes neutral. So how do we kind of design spaces with that in mind that can support its different conditions throughout the activities? They develop their own schedule of activities and really rather than a linear but more circular way of inhabiting the station and living throughout it across the four different crew members. Here, zooming into some of the details, a surgical suit that would allow to perform any sort of procedures on the human body with attaching equipment throughout, but also being able to enclose those space and work all around. From surgery, taking us to restoration, physical therapy, and recovery that may take on the outside ring. Again, using a lot of ideas for the resistance, with a built-in resistance, but also cycling and including a lot of those exercises within the ring itself. And this is a plan view, so you can see the central space for the surgery with the enclosure and the other ring on the outside for recovery and exercise and all sort of other type of activities and would be embedded more within on the peripheries. So here you can see another view of this proposal. We had students also then interested in personalization and sense of belonging. So what comes to mind is one of my favorite examples by Corey. He was studying all sort of effect on psychology and how people have different preferences in terms of temperature, in terms of light, in terms of sounds, and so on. So having understanding really these different needs for the human body, how does it manifest itself in a station where everything is standardized and designed for everybody rather than individualized. So his approach was really to think about how we can provide maximum amount of personalization, and that was done through thinking really about the atmosphere and an environment rather than just physical space. And he proposed this very smart tile that would actually have a different system embedded within it that would be for both heating and cooling, including light control and different type of lights, noise and noise machines and masking machines, sound machines, and so on. And when we think about incorporating that across the station or different zones of the station, the same space could be used for different functions and provide really comfort to or desired kind of effect to an individual. So somebody who, likes a cooler temperature versus hotter temperature, they can coexist almost within the same space or use the same space through within like different time frames. And that really opens up the idea that within this very small space, we can actually create all sort of activities that would accommodate the personal needs. So here are just a few examples, including a bathroom and sleeping and so on. And how that would then take place in the Starlab station. Recently, we were also really interested in the robotics and how we could support the work of four astronauts in space and add to their station other brains and minds, but also hands. So with the use of robotics, whether this is hard robotics or soft robotics that we see at the bottom, the students really thought about the different ways soft robotic could play a role in the station by studying different type of grips within soft robotics and suctions and gripping things through hands or different type of tentacles or hugging capabilities with inflatables and using that as means of people from Earth that could connect virtually to support the four people on the station. And here are just a few examples and details of this proposal. This is using inflatables for sleeping and this idea of hugging people and creating closed environments at the same time, taking it completely down and freeing the space. Here also proposals for how that could look like with the little tentacles coming out from different side of the walls, supporting the astronauts' work and being embedded into um, different parts of the walls and furniture of the station. So here one more full-on proposal of these different robotics and robotic skills, both on the outside and on the inside. And again, thinking about adding that sort of added intelligence, communication, and support. I'm going to pause here. There is a lot more. Again, a lot could be found in our research books, but with time, I'll stop right now. Thank you.
Amazing. Thank you so much, Marta. That was really fantastic. And I know that I appreciate whenever I get to hear you talk about your work in space architecture. I appreciate how creative the solutions that you and your students in your group look at and allow yourself to not be held within the boxes of what we've done in the past, but instead look towards the future of how we can really design for what we want in the future. We're now going to hear about another really incredible future thinking outside the box architecture and design solution from Chris Maurer from Red House. Chris, we're excited to hear from you. Thanks for joining us today.
Thank you so much. Yeah, and I'm going to do my best to try and integrate all the talks together from Michelle and Marta's amazing, design and user experience ideas to Karen's study of fungi. So we're going to try and integrate those two things. And the reason we're doing that is we do a lot of work with mycotecture that uses the growth of fungi to make building materials and to shape space. And we're engaged in a project now through the NIAC program, which is NASA Innovative Advanced Concepts. We're in phase 3 of that program. It's only the 5th time they've ever awarded a phase 3 out of the program that's been around since 1998. So they feel very positively about these concepts. But the idea here is to actually be able to grow buildings off planet. And that becomes advantageous because you can save a lot of mass transport, because you can take a little bit of biology, take that with you, and create, potentially tons or millions of tons of material using in situ resources. So that's the concept in a nutshell. I noticed that Dr. Dana Miller was talking a lot about the problems with mold and fungus in space, but I'll just note that we cannot live without fungi and we cannot live without bacteria. Our microbiome is very important, and I think we look at this as an opportunity to share space exploration with our little friends, our microbial friends, and leverage that to make structures at destinations. So this is the one I always start with. It's just an animation of what we're talking about here. So we're using inflatable structures that instead of having hollow shells to them, they have these bioreactors in the outer shell that enable the growth of organisms. So here you see algae growing in these clear reactors that make colonies that are enable fungus to grow on top of that and create a composite material. So we've made materials out of these composites that have literally built houses out of them. We make them as strong as concrete. They become great insulators, and they're radiation protective. So all of those things are huge benefits for developing structures off planet. And we look at doing that in a bunch of different ways. As I mentioned, that outer shell of the structure becomes these reactors. And if you look at our section drawing there, where you see the square forms there next to each other, those are growing microbes in them. And we liken those to spacesuits for microbes. So we're creating an Earth-like environment in them to allow those microbes to grow, and then they create this multifunctional material. We've developed lots of different archetypes for this. We worked very closely with Dr. Jim Head and Commander Dave Scott, who was the one of 12 people to actually walk on the moon, the commander for Apollo 15. They've developed a 500-day reference mission where we've put together 7 different archetypes that are part of that. We've looked at different orbital stations. There was a DARPA call recently, and we look at transitioning this technology to low Earth orbit, and we'll talk about that a little bit more, is another opportunity for this. But we look at this as a platform technology. You can use it to build just about anything, and there are different materials that are actually can be grown in these bioreactors. So the bioreactors become a platform for making different organisms and growing materials at destination. What's really exciting about this is, from an architectural standpoint, is this is the first time I can think of the materials are coming from architecture. Normally we think of the materials and we put them into our architecture, and there's a reciprocity that happens there. In this regard, the reciprocity happens backwards, and we have to think about the architecture as forming space and opportunity for our tiny friends. There are 3 ways that we're looking at that. So I'm mentioning there are micro-aerogels, micro-bricks, and micro-regolith. I'll start with the bricks, and this is what we do here on planet Earth. So as I mentioned, we've built structures using this process where we take cellulosic waste, we mix that with water and mycelium, and then we're able to make structural materials. So we built in a house out in Africa where we took this encroaching species of bush, used that to make food and materials, and the whole process regenerated land and stored carbon dioxide at the same time. So huge opportunity for what we're calling regenerative architecture here for us on planet Earth. And NASA has told us that they hold that project up as a point of pride, that they were able to have a company like that spin off to develop these processes. But it's maybe not the best thing to do off planet, because we don't really need these materials for structure, because we have our inflatables for that, and they have tensile strengths of 2 or 3 times what steel is. So these are really good materials for the structural capabilities of being inside of a pressure environment. And so the materials we're looking for need to be maybe better at insulation rather than structure. But we do have this in our palette of materials, and it's one thing that we note. Now, on to insulation. Aerogels are amongst the best insulating materials there are on planet Earth, in the universe, you name it. This is a process where you actually take a gel and you lyophilize that, or you basically switch out all the water that's in a gel, like Jello, and you put air into it. And so it becomes this material that becomes 98% air instead of actual material, which makes it a fantastic insulator. As we look at the mass trade for this, we can basically develop a material off planet that uses 98% in situ mass, which is mostly water, because we're going to combine the water with this material. We're going to grow fungus on it that's going to allow us to have biochemicals like melanin and other products that can help shield from radiation. And then we, at the end of the day, we're going to actually get that water back through lyophilization that we can leverage the space environment for. And this is a really exciting opportunity, because we're actually going to use the lunar environment, or use the Martian environment, to lyophilize these materials and turn them into the aerogel. So you don't have any energy involved with that. You're actually leveraging your environment to do that. We're able to do this because we're designing these novel bioreactors that have different types of exchange of nutrients and heat and gases. that allow us to do this in place. And here's a real small, quick demonstration of how that works out. So if you have your water and you drop that into one of these chambers, and then you mix that with a gel, you get a hydrogel that becomes a good substrate for growing mycelium on. This fungus can now go into that hydrogel chamber and create the biochemicals, the things we need, including melanin, which becomes a radiation shield for us. Once that melanin grows in there, it's going to change the color, it's going to deposit those chemicals. Then we release the air, and we're able to not only lyophilize that material, but we're able to extract the water that went into this process. So in this case, we're actually recycling the water when we do that. And that's not common amongst architectural and construction processes, I can tell you that. And as water is a huge, important resource, this is one of the things that we promote in this technology to be able to build off planet and be able to recapture water as you're doing it. So here's a few, samples, just by augmenting it with 0.1% and 0.2% melanin, you can see how much that material changes, and that becomes advantageous again for space radiation protection. Okay, and so regolith is another in situ resource that we have that we can leverage, and if we look at using this, we can actually go up to 99% in situ mass resource utilization. So this involves us growing spirulina at destination, or an algae, and you saw that in the first animation we did. That algae then gets paired with our regolith, which has no biological or nutritious elements to it, but acts as an aggregate. And then when we mix that with water and mycelium, we get a glued together material. And what you see there on the right is a picture of a sample that I have right here with me. And you'll see in a future slide. But what we're looking at doing is integrating the growth of that algal substrate for the mycelium into the architecture we're doing. And at the top there, you see some images from a researcher and a friend of mine, Kim, who's a researcher at South Carolina. And on the bottom there, that's Dr. Rothschild and myself demonstrating some of the actuation architecture that we've been able to build using these reactors. And on the right is the sample that comes from that. Here's a section through a building that would have those reactors embedded into the fenestration, which does a lot of things for you. You can use it as life support. You can use it to scrub carbon dioxide, create oxygen. The water becomes a radiation shield as it's growing, and you can also use it as a thermal management technique. So this becomes hugely advantageous in a lot of ways, and that's why we say we want our little friends to be part of our architecture, because they can do so much as we grow with them. Another image of a toroidal figure that has 24 buildings connected by some of these algal reactors. And I'm going to move into low Earth orbit because I think our time is short. But we basically looked at developing this, taking this technology to LEO, and imagining how many of these could aggregate together to become a larger space station. So with a payload similar to the size of Starlab, you could launch potentially 12 of these at the same time, because they would be compacted inside of a starship. Different things we've looked for LEO too, and this is with folks at Starlab, is we've proposed some options for having living walls that incorporate the growth of organisms in it for a biophilic sense, but also it becomes a science experiment where we track the radiation shielding and the insulation as a function of the growth of the organism. So you can see over time how much the radiation shield is augmented by growing these organisms in these basically petri dish type tiles. And we've also looked at different ways of making furniture for LEO and for space travel. So it's not just the architecture we're talking about here; it's the user experience, it's the the comfort. If you've ever moved your apartment or house, you know that the furniture is quite a bit of mass, actually. And so here we're proposing some inflatables that have our nyack black in it. So this is this melanin-rich fungus that we found is a very great shield for radiation. And it can be in these long duration spaces like your bed and your workstation. and things like that to give you extra radiation protection while you're in LEO. And there's an animation of it growing. But I want to point to the other aspect about sleeping in LEO, and we've looked at that with some of the other designs that we've seen so far. Is that right now on the ISS, what one does to secure themselves while they're sleeping is to kind of strap themselves to the wall. Here we have a process that can actually hold you into place a little bit more delicately amongst the dignity of what would be a future hotel in the sky, and you have the opportunity to have this NIAC black again as one of the radiation shields that holds you into place as it inflates. And here's just a section through a similar workstation that it wouldn't just be during the night you would have this, but during the day you could have a workstation that would help you stay into place so that you're not actioning your muscles to hold you into place as what happens with folks at ISS. You actually have to hold on to stuff to keep you into place. This could comfortably hold you into place while you're working, enjoying leisure time, and have the added protection of the fungal biome to protect you. And so I'm going to stop sharing slides there and hopefully kick it back to a joint conversation as we move through the program. So thank you.
Awesome. Thank you so much, Chris. That was really interesting. And I have to say, it was fascinating to see within the Leo designs the tie-ins with many of the concepts and ideas that Marta presented and how they might be supported in the future by NIAC Black and that really unique fungus. So that was very cool, and we appreciate you joining us for the session today. So for everyone here, we do have a couple of prepared questions that I'll go ahead and ask our panelists. But for all of our attendees as well, please, we want this to be interactive, and this is really about all of you. So if you have a question, feel free to either raise your Zoom hand or drop your question in the chat, and both Sam and I will be monitoring that, and we'll make sure to ask it on your behalf to our panelists. I do really quickly want to just ask before we start the panel, Dr. Nick Nastasi, who is our panelist but didn't give a presentation, to just pop on real quick and say hi and make a quick introduction.
Yeah, hi, thank you, Abby. Yeah, I'm Dr. Nick Nastasi. I'm a postdoc in Karen's lab. The bulk of my PhD work was related to what Karen was sharing there. So, very interested in space, very interested in microbes, and happy to be here and talk about it.
Awesome. Thanks so much, Dr. Nastasi. Okay, so while we wait for any audience questions to filter in, I will ask some questions that I'm interested in. So whenever I think about designing for space, I always think about analog environments here on Earth that we can kind of learn lessons from and then translate those into a space context. So I'm curious to hear if any of you have used those types of considerations of maybe looking at remote research stations or submarines, and what types of design and architecture concepts can be translated terrestrially to space, and what ones really fail when you make that comparison. I think that's mostly going to be for our space architects, Michelle and Marta, maybe Chris as well.
Yeah, I can talk about the reverse of that. What's really interesting is we first came up with some of the concepts for our mycotecture for humanitarian reasons. We noted that you can make food and housing at the same time. We can regenerate the planet Earth, which is a pretty important one too. But we struggled to get funding for that until I was presenting that at a NASA conference, and then met with Dr. Rothschild, and she said, "Well, I've always wanted to grow buildings off planet. Do you think we could work together on that?" And we were funded by NASA to do work on the moon and Mars before we ever were to try some of these things out on planet Earth. And what's really interesting is that the same conference the next year I was presenting, we're working on the moon and Mars for this type of architecture. And a researcher there is like, "Why aren't you doing this on Earth?" And then we teamed up and started developing the original concept, which was this humanitarian project. And that's what led to the project we did in Namibia that took bush and converted that into food and housing, regenerated the land, and stored carbon dioxide. So a lot of times I think, we look to organizations like NASA and for space exploration where we really understand that we're in limited resource environments and that things are harder there. We're not able to externalize things like the environmental footprint of our material and supply chains and things like that. So we have to think really carefully about circularity, and we have to think about resource utilization very carefully. And then when you do that and you can demonstrate that, then if you think of planet Earth as a limited resource environment, which it is, we just don't understand it that way, then that's when we get to really sustainable thinking and what we're promoting, which is regenerative thinking. So we can look at having positive waste streams that are coming from our processes and making a positive environmental impact as we're building things. So we think that this look to space and circularity and those things have been hugely advantageous for us to present things to people how we should be living here on planet Earth.
There is a fantastic book by Lydia Kallipolidi. It's called The Architecture of Closed Worlds, and it actually looks at 50 different precedents from the past on the extreme environments and closed systems. So I think it is a classic way to start a design brief by looking at precedents or everything that lives around us, and different approaches that usually go about thinking how we advance those. My take is always how do we critique those, and that's really a starting way of looking at the existing work. But I think when you design, this is one way to come up with new ideas through looking at the existing kind of precedents. And maybe what Chris is also showing, and it's another opportunity, is when you find an opportunity on an invention, right, on a material scale, and how then that impacts architecture. So that would be another means of entering design ideas. And maybe the third one is by problematizing. So really tackling a specific problem and really trying to think how you could tackle it. So I think there's different ways of going about it. And I guess it's just a matter of what's your preferable approach to design.
Absolutely interesting. That's such a great book suggestion. I will make sure to take a look at that afterwards. I loved what both of you said about this concept of designing for space or solving for space to solve for Earth as well. Okay, so we do have a audience question that is directly for Michelle from Journey. So it's a two-parter. So what is the timeline of Journey's vision? And how are Journey's goals different from its competitors? And specifically, what is Journey doing in a different way?
Sure, that sounds great. So I would say we're working with Starlab in partnership over the next couple of years. We're in a way kind of matching their HITL schedule, the human in the loop. There's a series of checkpoints that they go through for internal reviews. They're currently looking at layout. And then it gets more and more finer grain, higher resolution. You're zooming in on details as you go. So we're currently working through materiality. We're working through the digital twin to review different design options. We'll be putting people, ourselves and some of the team in the headset and looking at ergonomics and reachability. We'll be looking at lighting and surface treatment. So we will be on for the next couple of years working with Hilton and Airbus and all of the different partners to develop kind of from the environment to the case goods down to products and consumables. So for the foreseeable future. And then I would say our unique add to the project is we're very multidisciplinary. I'm an architect. We have other people on the project, that are a little bit more human-centered. We have digital artists on it. We have a whole varied background, and we come from all different industries. So again, it's the restaurants, the healthcare, food and beverage. There's all of these different sectors which come into play in very tight quarters in a project like Starlab. So I would say it's our unique background and the fact that we're able to bring all of these different perspectives. We're also really good listeners, and I know that sounds like a weird statement, but in our experience design, process, we really are kind of watching, looking, listening. I have never designed for low Earth orbit. I am not a space architect. So I think we are also benefiting from fresh eyes and perspectives. And again, bringing in this wealth of knowledge from other, human activities on Earth and helping imagine and translate that to space. But learning all the way from the experts that have been there and done that.
Thank you, Michelle. I can say that we're all really grateful to have you and all of your colleagues at Journey be a part of this endeavor in building a truly unique and next generation space station that takes into consideration the human elements of what it is that we're trying to do. So looking forward to all of those great advancements moving forward over the next couple of years before launch. So our next question is from James Davik. James, would you like to go ahead and ask?
Yes, hi. Hello, everyone. Yeah, real quick. Interesting presentations. I'm recently retired NASA employee. But I did have questions on, I guess this would be probably for Michelle, in terms of, you're talking about operating in space. What is and I think there was a chart on there that showed prior to operating in space, there's training. And what type of training is anticipated? I mean, we talked earlier about how, in the old days, astronauts were fighter pilots and scientists and everything else. And with probably in the near future, where a lot of people could be going into space, low Earth orbit, for hotels, space tourism. Is there going to be a need for training? I mean, obviously the environment's completely different. Johnson Space Center has the neutral buoyancy lab, but that seems to be restricted mostly for NASA astronauts or maybe SpaceX or European Space Agency. So when more people start going into orbit, low Earth orbit, what is the plans or thoughts for training them or getting them exposed to that type of an environment?
Mm-hmm. So just first off, I am not Starlab, the operator, so I can't speak from their side exactly what their plans are. But I think what we can imagine is the way that right now people are used to using Matterport to explore, new houses or apartments before they go see them. I think there will sort of be an accessibility wave where through showrooms, through digital platforms, through gaming engines, it feels like the public will just become more acclimated in general to life in space. The ISS does have a virtual walkthrough. I think it's probably a small sliver of people that currently know that exists. There are the ISS modules at the Johnson Space Center where small groups of people can actually train before they go up. So I think in a way, it will need to be more accessible and commercialized. There's probably some, augmented realities of something that's physical with a little bit of a digital overlay. The zero gravity is going to be something that's very hard to kind of practice until you're there. So I think Starlab will rely on some best practices, what's happened over the past couple of decades, but it feels like more digital tools will help us be able to practice the motions, understand how to use your, sleep sack before you get there. I'm kind of answering your question, but I think it'll be layering in technology and broadening the audience that gets to participate in that.
Okay. Do you think that if there was facilities available similar to the neutral buoyancy lab where people could, mimic
Yes.
that type of
Yes.
would you think that would be a training facility that might be used even just for the public or just like I said, general tourism?
For sure. I think the way that we're all used to boarding a plane, I mean, that's, decades from now that people would treat space travel and with the same exact familiarity. But it feels like there could be a privatized, training facility that's meant for the people that will be going up. And then there could be a more public version. If you think of the arcade games where you're on like a high wire or like trapeze artist school, there's ways that we can simulate some of that motion, and that may be, a wave of venues that rolls out to bring the public kind of into a special space where you can learn to feel what it means to be an astronaut, and you might be kind of training in some of the top 5 things that Starlab does in their space station.
Will these presentations be available? Or can we get a copy of those or?
Yeah, I can comment on that. So we're making the recording of the presentation available by request. So if you
Okay.
send us an email, any of the organizing team members, we'll make sure to put our emails in the chat before we leave, and they're also available on the registration website. We can share the recording with you for sure.
Okay, very good. Thank you
And
so
then,
much.
yeah, it was a really great question. Thank you for joining and for asking. I will just add a couple of additional points in there as well, in addition to Michelle's fantastic answer, which is that for current training for Starlab, we did just recently put a skill model version of Starlab in the Johnson Building 9 down in Texas. So that is a new development that'll be used for all kinds of, human in the loop testing as well as astronaut training and preparation for missions. And one of the big distinguishers, I think, with what we're doing with Starlab that's a bit different than, what we've previously done with ISS and Skylab and Mir and some of the others is we're really looking at creating efficient systems that reduce the amount of different types of situations that people will find themselves in. So, for example, Starlab is currently not anticipated to need or have EVA, extravehicular activity, or spacewalking opportunity to conduct repairs. It's being designed in a way where all necessary repairs can either be operated robotically or accessed internally. And that is a huge adaptation and efficiency adjustment for the training that's necessary before astronauts go to space. And then, in addition, looking at how we can design those interior spaces to, for example, have less dust accumulate and have fewer of those types of situations that astronauts need to be trained to operate within. So if you're interested in continuing the conversation around training for space, the visions that Starlab has for that, as well as ongoing research and efforts within that sphere, we are actually hosting a workshop on April 17th that is all about advancements in training in space and for space. So as a registrant for this workshop, you will receive an email invitation to join that one as well. And we can definitely talk more about some of those specifics with another group of really great speakers. Okay, on to our next question. This one is for Dr. Dana Miller and Dr. Nastasi. Does fungi's activeness in space increase linearly with moisture, or is it more complex than that?
So I'm really excited about this question because that's actually the place that we originally started this work with a grant from NASA to look at actually modeling microbial growth based on moisture availability. I'm going to put a link to the paper that resulted from that in the chat for anybody who wants to access that. But Dr. Nastasi and I worked on that together with our collaborators and actually developed a fairly complicated mathematical model to predict how much growth you would get in a particular situation if you know the moisture, and especially if that moisture is going up and down because it might not be necessarily at the same level. So anybody who wants can take a look at that. Feel free to reach out to us with questions. It's a somewhat complicated model, but you can see that and just let us know if you have any questions. And Nick was actually the one to do the microscopy. So for the second part of the question, I'll let him take that one.
Yeah, so I wanted to add with the activeness. I'm not sure if you were talking about the metabolic stuff or like fungal growth, but yeah, so we tested it 2 ways, like a constant relative humidity. So it remained at a constant like 50 through 100% in different chambers on Earth. And we found that it did not start growing until about 80%, and that's when it would start to grow a little bit. But 85 and up, it just skyrockets in active growth. Um, and the time of wetness modeling, which is that varying, actually caused even more growth and more rapidly compared to earth dust. We think primarily because of the texture of it. It's more like akin to dryer lint up there, so it's very absorbent and is able to pull the moisture out of the air more readily, which makes that water available for them to use and grow quicker. For the microscopy part, was that for monitoring it? I'm sorry, I can't see it in the chat here. I forgot what you said already.
Hold on, I can read the microscopy question again. So it is, I noticed that lots of images presented were from microscopes. How could microscopy play a major role in live mold measurement?
Yeah, so that is a tough one. It is common on Earth to do that. A lot of like mold remediators will take air samples and spore traps, and that's how they will decide if there's a problem in your home. But again, that's looking at species, and as the presentation was mentioning, like we're moving towards the function part, which a microscope would not be able to tell. And also, like if you have a visual spot that you can swab and put it on a microscope slide, then you could obviously look at it. But if you're trying to monitor just that unseen part, like where is it coming from? Like it really depends on where you're sampling, and you don't know if that surface swab you happen to utilize and put on the scope doesn't show it. It doesn't mean it's not in the habitat anywhere. Um, so we actually use dust as a monitoring source too. We didn't talk about that there because on Earth, everything eventually settles into the dust, and in space, everything will be pulled through the ventilation system onto the HEPA filter covering. So theoretically, if it was in the habitat, it's also in the dust somewhere. So you can kind of use that as a monitoring source as well. But the microscopy is not trivial, and I'm not sure how easy that would be in microgravity either, but it's definitely interesting. I would like to try it for sure. Thanks for the question.
Awesome. Thank you so much, Dr. Nastasi. Okay, so our next question is for Chris, and it was already answered in the chat, but I thought it was really interesting, so I was going to ask it here as well. So it's how would you contain the microorganisms in the structures that you mentioned developing so that they don't potentially contaminate the remainder of the environment?
Yeah, that's a very good question too. Yeah, and I'm trying to keep up with the chat over there, but I might miss some, so please, I put my email in the chat there too. So if anyone has questions afterwards, please do. But that's an important thing. Planetary protection is a huge thing for the moon. NASA and the space agencies aren't as concerned about it as Mars. And the reason being is because on Mars we think that there's no life there. We think there's no living organisms there. And so if we go up there and we start spreading organisms all over, we're not worried that they're gonna like take over and grow everywhere because the environment's pretty inhospitable for that type of thing. But what they are worried about is, an astrobiologist finds a rock that has a spore on it, and they're like, well, I guess life has been here, for billions of years, and it turns out came from our building. So that's one thing to worry about. There are ways to control for it using the architecture, and I call that triple bagging, but it's basically sealing up the cells so that they could not escape. So that that's the first thing. But accidents do happen, so there is a possibility that something could just get ripped apart, and then the organisms could fly out there. So there are synthetic biology ways of dealing with that and making the organisms so that we have like a barcode written on that, and it'll actually have like a little thing that says that this organism belongs to NASA. So if an astrobiologist finds that and they say, oh, I wonder if this is a 3 billion-year-old microbe that's been here forever, or if this is something that came from that building that got destroyed in the windstorm, they would know right away. And there are ways of actually making it so that it's inert or it's sterile, that it could not reproduce in any other conditions than what you had addressed it for. And so there's a lot of fungi that are that way naturally. They would have to link up with a certain mate to be able to create spores, which would enable them to reproduce. But theoretically, you could take one mycelium and have that grow forever and be its own organism, but it would not produce a spore or a fruiting body ever until it meets up with another form of DNA that has a sexual partnership or something like that. So there's lots of ways to do that. That's above my pay grade. That's Dr. Rothschild and et al. But we are very focused on that, and it becomes a thing that NASA Planetary Science Department, his whole department, deals with, and they're looking at very closely. The reason the moon is less worrisome is because it goes down to like negative 200 degrees Celsius and up to 100 degrees Celsius on the surface. It's very inhospitable to life. And there's already, we've already had human beings there, which are the biggest vector for contamination. As I mentioned in the chat, you and I have trillions of microbes growing on and in us, and anywhere we go is going to be exposed to those microbes, and we can't clean ourselves of those, or we wouldn't be able to digest our food or fight infections or do normal metabolic processes. So we need those microbes. There's no way around that. So the fact that there's been 12 people on the moon, they actually left their poop there. So a lot of microbes in that. There was an Israeli lander a couple years ago that crash landed into it and was full of tardigrades, which are these water bears and these little animals that can supposedly survive a lot of things. Who knows if they can survive the lunar night and lunar days? But that there are already contaminants on the moon that are more than likely completely sterilized because of the environment that you see there. But yeah, Mars is another story, and that's where we look to all of the check all of the boxes for planetary protection.
Yeah, that's a great point about how inhospitable the moon is as compared to Mars. And another consideration to take there is the fact that most life here on Earth is adapted to a very specific set of atmospheric pressures and exist and thrive under. And there are only a couple of microorganisms and such that have been identified here that would be able to survive under lunar or Martian conditions.
Yeah.
Which really does make it a little bit less of a concern, although planetary protection is still very important. I can definitely imagine what a bummer it would be for an astrobiologist to find a microbe on Mars and then think that they discovered alien life for the first time and then find out that it's Chris's fungus. That would be a bummer. But we have another question for you, Chris, actually, if you don't mind staying in the hot seat, which
Sure.
is, would you have to replace the mycelium-based blocks after a certain amount of time due to radiation exposure? And considering how challenging the environment is on Mars, how would that occur?
Yeah, that's a good question, and that's one thing that we're looking at. So I don't know the answer to that now, but what we are studying is we're taking things like these melanin-rich fungi, and we're putting them through radiation testing regimes. But as we do that, it costs about up to about $12,000 per hour to expose them to the radiation here on planet Earth, because we have to use these simulators. So obviously we can't do that for weeks and months and years as you would want to do on the moon and Mars. So the best way to do that would be to test this in the space environment for that. We have sent materials to the space station, on the outside of the space station, where they were exposed for over a year, actually exposed for 6 months, but in the space environment outside of the space station for a year, and we test the long-term effects of that. So that the impact of the radiation over time could actually degrade the materials, and that's what we're looking at through simulations and different things like that. But it's a really good question, and we're working with researchers to try to find that answer. But it's really hard to do unless you can actually be on the moon for years with the material to do that. We may be lucky enough to be a part of a CLIPS mission soon, where we're going to be sending materials to the moon, and they're going to stay there because there's no way of getting them back. But our instruments are going to die during the lunar night. So as people on this call probably know, that nothing can really survive the lunar night right now. Any robots that go up there and are on the lunar surface are going to die throughout the night. Which is these near absolute zero temperatures, because it gets so cold that so the instruments won't work, but our materials will be there. We could check them, potentially a decade from now, once somebody pays for a return trip or something like that. So there's a lot of ways we can look at doing that, but it really comes down to having the cost for testing such a thing is prohibitive at this point. But our expectation is that we will have to switch out the materials over time, and that's where the ability for this material to be a compostable material is pretty advantageous. So we can use that as the soil for growing plants and other useful things. Can be recycled into other objects, and so there's a benefit of these being living organisms because then we have this carbon that we can recycle in different ways. Producing these carbon-rich materials is going to be important for more than just architecture. In fact, most researchers that look at making carbon-based materials off planet, they're thinking of food and they're thinking of different ways that we can create digestible material. So that's what we think we would do is figure out a recycling program for this, and then utilize it again in a closed loop system, cradle to cradle, ideally.
That is the name of the game in space, right? Is
Yep.
closed looped and
Hmm.
circular economy of
Hmm.
material. Absolutely. That's super interesting. Thanks, Chris. Okay, so another question that we have in the chat, and I think this one looks like it's probably for Michelle, is what science or data are you collecting when you're designing the internal experience within Starlab? For instance, it's nice to say that a certain color tone in the lighting makes someone feel better or that less clutter is more pleasant to look at, but what types of metrics are you using to quantify these and other quality of life environmental decisions?
Yeah, that's a great question. And I would say we're at the stage now where we're kind of designing that. And then maybe the back end of this year going into early next year is when we'll start to validate that. And I would say it's through a couple ways. It's not just us. We'll have a couple other partners, enlisted by Starlab to help. But I think this is also where simulation and A/B testing will help. We will put forth proposals, but then you're able to put, humans and astronauts into virtual or physical environments. I'm just going to say all red or all blue. That's not it, but let's just say that there's different palettes or different environmental conditions that are being tested. And the way that they do the HITL testing, the human in the loop, you're probably measuring both like cognitive, are they able to complete tasks, differently or at different rates or to different levels of success? There's biometrics, is it visual fatigue, heart rate, body temperature? We're hoping to have a couple different ways to test. I'll say there's benefits to having a more neutral base palette. The ISS is currently all white. So something that we know is not a visual strain right now could be a good starting point. And then I think we're going to use color very thoughtfully. Right now it's for footholds and handholds, emergency signage. So I don't picture Starlab being a fully saturated environment that will be a lot for someone to kind of acclimate to and live in for 6 months. We also have talked about crew provisions and bedding in the crew quarters being customizable by the occupants. So in a way, they're kind of choosing their own, environment in which to live. So there's a couple different ways I would say that we're going to move forward with it. In order to make sure that the team collectively makes the right decision. Um,
Yeah, that's really interesting. And I think that another one of these important considerations, Michelle, that whenever we think about and talk about Starlab right now is that the intention for Starlab in the near future is for it to continue to be a research-oriented
mhm.
facility where we're making a lot of improvements to improve the experience of astronauts on board. But Starlab, as it currently is being designed in this iteration, is not intended to be, for example, a hotel in space, right? And so I think that that's interesting to hear about the different potential utilizations of color in space, and looking forward to hearing more about how that progresses over the next couple of years as that type of A/B testing and such goes on. So thank you. For anyone who is interested in hearing more, I have to do the requisite pitch, right? Anyone who's interested in hearing and discussing more about psychology in space and how an environment can impact the emotional and mental health and experience of an astronaut, we will be hosting a workshop on March 27th that is specifically focused on psychology in space. And we'll be inviting experts to come and talk on those subjects. So hopefully you'll all be able to come join us for that and we can continue that conversation. Okay, so we have a couple more questions in the chat. Let me see what we've got. Um, I see a question from, let's see. What exercise countermeasure systems are being implemented, and how is musculoskeletal and cardiovascular deconditioning being tracked on Starlab? I'm going to go ahead and say that, again, another pitch, my apologies. That question will be more appropriately answered at our next workshop, which is on February 13th and is specifically focused on medicine in space. Today, we have people who are more looking at design and habitation challenges in space, but next month we'll have experts who are talking about the medical challenges and solutions for space travel. And I think that would be really well suited for that. So hopefully, the asker of that question can join us then, and we can chat more about that. We do have another question in the chat that says astronaut training can take multiple years. When commercial space training expands for public, what is a realistic minimum training timeline and which competencies, medical emergency operations, systems can't be compressed? Um, I'll be the first one to actually jump in and comment a little bit on that question. And then if any of our panelists want to add to this, I think that would be great. But my experience in the space industry is that it really depends on the complexity of the mission, of what type of training, the duration, and what can and can't be compressed. So, for example, if you are developing a 3 day long mission, that doesn't include significant amounts of research or other uh, operational capabilities like that, that's going to be a significantly different type of training that's more about safety and experience and could be compressed to maybe 6 to 9 months. Whereas if you are looking at a 6 month or a year long stay on the International Space Station or on Starlab or on another LEO destination, that of course is going to need to be a longer training that includes a lot more depth and complexity in it. And so the current timeline is about 2 to 2.5 years of full-time astronaut training for that 6 month block. I anticipate that we'll probably have similar training in the future. And then in addition, it also takes into other complexities, not just the research that you're accomplishing in space, but as we mentioned previously, whether or not you're participating in extravehicular activities or spacewalks. That's a whole separate side of training that can add to that training time. And then in addition, you have to consider all of the abilities and skill sets of the additional crew members. So if you have a larger crew, not everyone has to be an expert in every, medical situation that might arise. But if you have a smaller crew, then everyone needs to be able to handle every single type of situation. So lots of factors that go into that. It's not an easy answer. Um, yeah, would any of our other panelists like to comment on concepts around astronaut training?
I do not have an estimate for durations, but I guess my comment is more just if the operating model changes. Like right now, everyone that would go up and goes to the ISS is a 2-for-1 or a 3-for-1. Like they're multi-talented, they're medics, they're pilots. They are meant to both, perform activities and take care of the station. If there becomes an inflection point where it is more like a cruise ship or an airplane, and there's a crew, like a permanent crew that hosts, and they're meant to do more of the difficult tasks. And then there's room for, guests or people that have received less training. That would just be a completely different operational model, which could compress, obviously, the training time that I, as a civilian, would need to go up for a certain period of time. That's all.
Yeah, absolutely. Yep. And those are all things that the commercial industry and how space tourism and commercial space flight operate are rapidly changing. They're different now than it was 5 years ago, and it's different even than commercial space tourism was 5 years before that. And the expectation is that 5 years from now, it will once again have progressed in a way that none of us can really fully anticipate. Although sometimes I do wish I had a crystal ball. We don't know what that future is going to look like right now. So that's a great addition, Michelle. Thank you. So another question is, and I think this is an important one both for our architects and designers and also for our microbiologists here is when you think about these missions that could be short duration versus long duration, and looking into the future where we might have extreme long duration, multiple years at a time, thinking, very long-term future of someday humans on Mars and such, what type of habitability conditions or considerations do you have to make for a short-term mission versus for a long-term mission?
I mean, I can say it's if you're going for long duration, you're talking about, major moments of your life. So I think just for us, it's building in variability, seasonality, things that we very much probably take for granted here on Earth. Just finding some way to either recreate those or expand on those for longer term missions compared to
Yeah,
short
getting
term.
back to that concept that you had mentioned of an astronaut who told you it's not boredom, but it's tedium, that we
Yes.
have to pay more attention to creating an environment that is uh, capable of supporting the human brain and experience through that type of longer duration mission.
On their current missions, they do recognize the workday and the work week. But I think it's the idea of, again, like months and years is something that would need to be considered. Yeah.
Very interesting. Dr.
Yeah,
Dan,
there's.
oh, sorry, Chris, go ahead.
Yeah, I was just going to mention that there's obviously the technical things you have to worry about, like radiation dosage and things like that from long duration that are different from short duration flights. But one of the things we really promote is the biophilia that comes with the living materials, and being around a nature-based environment is something that's not really accounted for and usually in LEO or designed for from what we've seen on off planet. So it's one of those things where I think that psychological comfort isn't really taken into account enough, and so that's why we push really hard for those types of things. But yeah, there's everything from the radiation dose, which a long-term stay is a huge component of that. And you have to have the materials that are much thicker and have different types of hydrogen bonds to block from particle radiation, and then you want thicker materials for electromagnetic radiation, which can be problematic too. So there's a lot of different aspects that one would deal with just in terms of dosage and time. But the psychological comfort is I think the biggest one and the hardest one to really understand for, and the one that I would say that us as designers are really most interested in, of course, developing user experiences.
I also think another one is to really think about the sense of belonging. And on a short-term mission, you may just manage, right? But on the longer term missions, you're going through holidays, you're missing out on a lot of things that are taking place on Earth. But that idea of a sense of belonging, both personally versus and also collectively, I think that's an important aspect to really think about. Right now, I think the astronauts are only allowed to bring in very small amount of personal belongings. So how do you create that space that actually makes you feel like you're at home?
Yeah, that's a good point. That's a really great point that when you think about that short term, there's a lot that we can put up with for a short term that changes in the long term. And it also, when we're thinking about that, I think it's so interesting to think about how food systems will impact that in the future as well, because that's a big part of the human experience. And as we improve our capabilities in growing and producing food in space, I think that will play a role in the human experience within space and such. So very interesting ideas. So there is a
Oh,
question here.
can I jump in on that one too? Also, real quick. Sorry.
Thank you,
Yeah.
Camilla, please.
Yeah, and so I think for the long duration missions, from what I think about is also early identification of problems. So it's going to be a lot harder to solve some of these problems. So, for example, when we had the problem with the panel in the International Space Station, we could dispose of that and have it replaced from Earth relatively easily. But something like that would be a lot harder if you have a longer term mission. So understanding early when there is an issue so that you have time to resolve it and not having these microbial problems associated with things like wiring or window seals or anything like that, because you could end up in a very bad situation if you let things get out of control. So I think thinking of ways that we can know rapidly, even before we know with our senses or something that might be hidden, if there is a problem, both microbial and otherwise, for a lot of these longer duration missions.
Yeah, I think that's a really good point. Thank you, Dr. Dana Miller. And it reminds me of a lessons learned that I got to attend at NASA once about looking at the past of inopportune moments in space and what we can take from those towards the future, where there was an instance of unchecked microbial growth occurring within some water tubing in a system on the International Space Station that there was no built-in way to monitor that. And so when it was discovered, it had done a lot of damage at that point. And so the more that we can integrate into our future space habitats and systems, built-in monitoring or other creative methods to determine when a problem is occurring before that problem gets out of hand, the better. I think there's a really interesting startup that I heard about recently that's looking at surface materials that can be placed in high contact areas that change color when there's early stage microbial growth that happens. And the capability of using that both in space, but then also in terrestrial applications, such as in hospitals or in other high risk areas for people.
Yeah, and absolutely. And one thing about indoor environmental quality is on Earth, people tend not to think about it until it's an emergency. So a lot of times it's a wildfire or some other issue, and then suddenly it's an emergency. And I think we don't have the luxury in for like a long-term mission of waiting until it becomes an emergency to deal with it.
Yeah, that's a great point. Just thinking ahead rather than thinking in a reactionary manner, for sure. Super interesting. Okay, we have another question for Marta this time. The architecture that you describe and design is incredibly personalizable. However, a lot of these designs necessitate extensive behind the walls utility. How do these designs allot space for specialized static workstations, for example, research, internal infrastructure, external systems, etc.?
So maybe just first, our approach is definitely very different than working on a specific projects for a specific client. We really treat the design as a think tank. So the way I would ask a student to think about their problems or proposal is actually to think radically, to go to the maximum and push that one specific concept as far as they can. And I'm not saying this is something that would be, applied or feasible, I think, but the idea is that you push really hard. So when you actually think about the application, you can always scale down, you can always reframe your project. But even in that regards, the students were thinking about not applying the smart grid everywhere and maybe having some space and zones that would be more focused on temperature control versus the other one on lighting, like, for example, workstation that would support a different type of work that you're doing, whether it's a focus work or it's a collaborative work, and also maybe mimic more of a circadian light here on Earth, because with Starlab you're orbiting 45 times a day. So that light is definitely limited, and that light you have it really disturbed in terms of biology. So I think having the level of control could maybe bring it some of a rhythm and also support like really your best work. And also, like, for me, in terms of personalization, it really goes back to the most important idea for me, that is flexibility. You have a very, very small space. So having things that are just fixed and designated or dedicated to one specific program may not be necessarily feasible. So how do we deal with flexibility? How we incorporate some aspects that are more fixed versus the ones that are could be adjusted, and that may go with example of the workstation, that you may need a small space where you place your laptop and you're working on something or communicating with someone else that is fixed and designated, but then the environment around you and the atmosphere around you is changing based maybe on what you're working on or what time of the day it is for you in a particular moment.
Thank you, Marta. Yeah, that was great. Okay, so I did just want to put out a last call for questions as we are just a couple minutes before our wrap time. And as much as we are enjoying this conversation and such, I want to make sure that we're super respectful of the time of all of our speakers who have already given us 2 full hours out of their day. Thank you so much to all of you. So for our attendees, if there are any final questions, please drop them now and we will try to get to them. But in addition, I do see a question for the host asking if there's a page that will list the presenters' email addresses from the panel and from previous workshops. So right now we are not listing those on the page online, but we can provide them by email. So feel free to reach out to the organizers and we can connect you with the presenters if you want, if you have continuing questions or would like to follow up on any of these conversations and discussions. So as a reminder, I'm one of the organizers. I'll go ahead and put my email in the chat right now. And Sam Shattuck is our other organizer. So we are both happy to assist with any of those connection requests after the event. Okay. All right, perfect. And then I think we have time for maybe one more question, which is for everyone on the panel. There's been growing discussion around the need for bioregenerative habitats in space. Is anyone currently conducting research or working on projects in this area?
Yes.
And we're talking
yeah,
to Chris.
yeah, that's what I was presenting. But yeah, the concepts we're looking at doing is having living materials that could potentially regenerate, and we've imported that technology back to Earth. And not only can we make materials that are more sustainable than conventional building materials, but they actually regenerate the environment here on Earth, and do things like store carbon dioxide and regenerate land, and so mitigate greenhouse gases at the same time as mitigating deforestation and things like that. So we would consider that regenerative. I think the question as to if we're going to have to recycle our materials, we kind of pointed out that could be a regenerative process too, where we're actually taking the materials that are grown inside of the architecture. Again, the reverse of what you would normally do. You'd make a material and then you build your architecture. Here, the architecture makes material, and then that material could be regenerative in the sense that it becomes fodder for growing more food, becomes the substrate for growing other things, and it just becomes a biological circularity that becomes regenerative in aspects. So I think we would point to that and say that that's our goal anyway. We're trying to hit those marks, and we are testing that through missions to ISS, potentially to the moon in 2026 and 2027. Testing these technologies for the ability for the microbes to actually grow in these environments. Creating the spacesuit for microbes, as we call it, creating the Earth-like conditions inside of these encapsulated things that allow us to grow these materials that can become regenerative, or I would consider it on the moon and Mars to be generative rather than regenerative, because there's no life there. Here we're talking about keeping life going and preserving life and augmenting life. There we're talking about actually seeding life, and this the first time where architecture and design gets to be the bringer of life rather than what is mostly, unfortunately, been through the history of design and architecture, the destruction of the environment. So here we're actually seeding life through this generative architecture rather than regenerative, I guess is how I'd answer that question.
Yeah, that's really great, Chris. Thank you so much. And I agree with that. It's an interesting perspective. And I really like how you consider bioregenerative or biogenerative in this case as not producing or fully recycling a material to serve
Hmm.
the same purpose through every iteration, but rather
Hmm.
considering the full lifespan of a material and thinking, what can it serve? How can it be utilized at each of those instances? Not always as a building material, but moving on to becoming a composting material or a food source or et cetera, et cetera. That's really interesting. I would say for that question asker as well that there's some interesting work that you can explore out there around the use of biomaterials and bioregenerative systems for environmental control and life support as well. So specifically, I think there's some interesting research that's ongoing about utilizing different types of algae as a component of these environmental control systems for future space habitats and looking at how we can utilize the dual properties of oxygen production, CO2 scrubbing, and radiation protection within algae's to create more efficient systems in space.
Yeah, on that point, there's another NIAC, so that's a program we're in called Water Walls that was developed maybe about a decade ago. The PI on that was someone named Michael Flynn, not the Michael Flynn from the first Trump administration, but a researcher at NASA Ames, and we're incorporating that life support system into some of the algal reactor work that we're doing now. Lynn Rothschild happens to be very close with Flynn et al. From the water wall projects, but that's a really good one to look at. And all of the NIAC projects have their final reports online, so you can check that out. And if you just Google Michael Flynn water walls, you'll be able to find that one.
Awesome. Thank you so much for that hint, Chris. Appreciate it. So this does bring us to time. I want to say a really sincere thank you to Marta, Michelle, Chris, Dr. Dana Miller, and Dr. Nastasi for joining us today. Your presentations and all of the great discussion that you have led during the Q&A were fascinating and I think really meaningful to our research community. So thank you for that time and energy that you've spent with us. Thank you to our organizing partners at the Human Performance Collaborative. Sam, Jess, who's not here today, but has worked hard on this, and Dr. Hagen, we couldn't have done this without all of your incredible support and work. And then finally, thank you to everyone who has attended this workshop and who has spent these past 2 hours thinking really out of the box and asking the big questions about the future of space exploration. It is you, the research community, that is in charge of driving forward what we do and how we do it in the future of space. So we appreciate the time and energy that you've come spent with us today and hope to see you at some of our future events. So as a reminder, our next workshop event will be on February 13th. It will be hybrid in person and online. Hosted at the Ohio State University in the BRT building, and the focus will be medicine in space. Following that, we will also have workshops in the near future on psychology in space and advancements in training in space. And then in addition, at OSU this April, we will be hosting the National Academy of Engineering Regional Meeting. And the topic of that this year is the design challenges of space and looking at the engineering and design challenges for space exploration. So hopefully we'll see many of you at one or all of those events moving forward. We've got a lot of great space conversations ahead of us. And with that, I will release the class. All right. Thanks, everyone.
Thank you.
Thank you very much.